In this short video demo, I'm going to showcase the usage of this GPU compute control panel that supports scheduling and auto-scaling and doing cost analysis for some of the different kind of GPU tasks. So which can be composed of either a training task, an inferencing task, or is low prioritized the batch tasks. And the ultimate objective is to maximize the amount of launch jobs with minimized GPU costs, which is calculated in a on-demand manner. So the control panel is for heterogeneous computer fleet. It's exposing 9 spec APIs over fast, and also with a background ticker that drives a virtual accelerated clock for the simulation. So let's take a look at the control panel on the top. We can see that there are all different kind of cars that are being listed here, and also it's showing the status of those cars, and as well as the cost per hour. So let's quickly launch this Docker image, and then we can have this control panel up and running. So in the meantime, we can use these demo scripts to launch some of the tasks. So if I run demo batch here, and so we can see at the very beginning, and when the clock is being accelerated 5 times, and all the GPUs are free at this moment, and then there will be a summation for the training jobs, where the 32 GPUs is being used that spans over 4 NVLink bundles that compose of a size of 32 cars total. So one of the principles that I've applied here is for training kind of tasks. So it is always respect the NVLink bundles. So which means we would like to put the training jobs into complete bundles as much as possible. So the reason of doing that is to make sure that we can make better utilizations of the NVLinks on each of the bundle to accelerate some of the training parallelism mechanisms. And the other kind of a task we support is to run the inference jobs. So we can see for the next task, when the task is launched for 4 different cars, since the runtime GPU utilization that is being calculated indicates that it's experiencing low usage, and so it's automatically scales from 4 cars to 2 cars, which will be sufficient to support the online QPS while running a reasonable amount of GPU. And so we can see that the estimated utilization is raised to 51% compared with original values. However, when there is spikes that are coming from online, so for example, if the QPS is increased by 20 times, and then the autoscaler is going to increase more cars. So basically, we want to control the utilization between the lower bounds and the upper bound to make sure that we have sufficient amount of GPUs and we're able to support the online traffics. And so the same story happens when the QPS is dropping, and then the autoscaler will recalculate the utilization and scale the number of GPUs down. And also, we're going to simulate the cases where there is a failures for some of the cars. And once one of the single cars is failing from the training, and then it will automatically launch another one based on the earlier strategies that we want to fix on 32 cars or fix the training cars in a certain range. So when the car is lost, and there will be new car that are being launched. So one of the drawbacks here is that when new car is launched, so it will be spilled into new bundles. So which will break our original design for feeding the training jobs into complete bundles as much as possible, which might potentially cause the fragmentations. However, we will compensate this by trying to launch the later inferencing jobs on these fragmented components as much as possible, so can reserve the rest of the bundles for more complete training tasks. So the next thing that I want to do is to launch another job, so which is chief of the non-urgent batch works. So this will be preferred to put on the low cost clusters. So we'll choose over L4 since the price is lowest, and it also comes with the relatively lower priority, which has been set to A for now. So meaning that it can be interrupted at any time. And the other kind of a job that we place here is when there is a high priority jobs that is taking over, and then it will take all the A100 cars here, for example. But one thing that we need to mention in here is that the strategy is to lower down the priorities once it scales up. So it's not going to maintain its original priority because the more cars it's going to take, and then the more chances that we can borrow some cars back from the cluster. And so, for example, if there are new training jobs that we will also like to launch on the A100 GPUs, and we're not going to make them pending forever, but rather we would like to borrow the certain amount of 32 cars from the A100 clusters, while keep the rest of the inferencing job running in the same time. So this is another principle in consideration, which means even when there is high priority task that getting intercepted, then it's not necessarily the queue the running inference jobs because we want to prioritize the inference job to serve the online requests from the customers. But here we're facing one of the situations is that we want to let the system to automatically examine whether it is possible that we can spill some of the jobs from the existing clusters to the new type of cards, especially when there are cases that we cannot handle all the traffics that are coming from online. And so in this case, there will be spec traffics, and so we'll launch the new tasks based on the online QPS. So as we can see from the right side, so the online QPS is increased from the original one to 200, and it is totally saturated and it's not sufficient to run on the A100 clusters. So thus, we can grow that on a different clusters, which is the latest task 007 that is running on B200. However, when it's approved and the online traffic is not sufficiently to be handled, and then the further consideration is that how we can spill over these two even lower cost cars on H100. And in this way, and we can handle the online traffics in a timely manner as well as minimizing the cost. And also there will be APIs that allow us to test out the terminate and resume some of the training tasks. As we can see that when the training tasks are completed or is resumed, and it can complete and until the training has been finished. So at the end of execution, there will be a summaries for all these costs. So we can see that the tasks that list with the different priorities and also the relative cost will be listed on the right side. So with reference to these numbers, the strategies for rescaling can be adjusted accordingly. Okay, thanks very much for watching.